Hello, this is the second lecture in the inflation series. What we're going to do is present more involved examples. We're going to present examples using constant dollars and actual dollars. And we'll also present an example with differential inflation rates and do the after-tax analysis. So let's see how to proceed from here. Very quickly, example number 2 is for a retirement plan. We wish to save by making annual deposits into a savings account so that the accumulated value is $1 million for retirement. Now, is $1 million enough to retire? Well, that's up to you. How much do you want for your retirement? Let's consider a time period of 30 years for the savings. And let's say, cautionary and put our money into low-risk investments which might have a real interest rate of 4%. Now, if the inflation rate is going to be 3%, then we have to consider what the market interest rate might be for that type of investment. The $1 million, of course, should be in constant dollars, because if you suffer inflation for 30 years, $1 million today won't be worth that much in the future. So let's think about $1 million of purchasing power today, which makes this constant dollars. And the question is, how much would the annual deposit be into the savings account? Now, there are two ways to solve this problem. Well, actually more ways than two, but we're going to show two particular ways. The first method is to do the analysis in constant dollars and then apply a series savings factor, the A/F factor, to obtain a uniform series of deposits that are measured in constant dollars. In other words, every year we're going to give up so much purchasing power, and that purchasing power is going to be the same every year. So then we can apply the real interest rate, 4% factor. Take the $1 million, apply the A/F factor, 4% for 30 years, and then that gives us $17,830. That's the constant dollar deposit we have to make each year. The actual deposits will vary, of course, because of the inflation rate. With inflation at 3%, the first deposit will be $17,830 times 1.03. That's really going to be $18,365. In the second year, our actual deposit will be the original constant dollar amount factored up for 2 years of inflation. So that's going to be $18,916. The purchasing power we're giving up is the same each year, but the actual dollars will be greater because of the inflation factor. And so on. In the last year, the $17,830 would correspond to $43,278. The actual accumulation then would be as follows. Our first deposit was $18,365. That's the constant dollar deposit with 1 year worth of inflation factored in. Our real interest rate is going to be 4%, and this particular deposit will earn interest for 29 years. So 29 years later, from time 1, the end of the first year, to the end of the 30th year, that's going to result in $134,970. That's just the first deposit. The second deposit will be $18,916. That's going to earn for 28 time periods at the real interest rate. So that's going to contribute to our retirement fund $129,779. And so forth. The third year, $19,438. That's in there for 27 years. The 29th year deposit is $42,018. That only earns interest for 1 year, so that doesn't contribute quite as much. And the last year, of course, the money really doesn't have time to earn any interest. It just transfers through. So that gives us a sum of $2,427,262. That's more than the $1 million. We need to make a check to see if that's equal to the $1 million in terms of purchasing power. So we take the $1 million in today's purchasing power, factored up with the inflation rate of 3% for 30 time periods, and lo and behold, we do get $2,427,262. So if we use method 1 and make that series of actual dollar deposits, our bank account will then have $2,427,000 and something in it, and that will then represent $1 million of purchasing power. Now here's another way to do it. we might know that there's going to be inflation, so we might figure out what the amount would actually have to be. So method 2 is a different method. Let's perform the method in actual dollars and apply the A/F factor to obtain a uniform series of deposits measured in actual dollars. So this series is going to be different from the first one. And it doesn't matter whether you measure it in constant dollars or actual dollars, it's a different series. We first have to obtain the desired accumulation. Well, we've already done that type of arithmetic, but we'll simply present it here again. We take the $1 million purchasing power now. 30 years later, we want to have $2,427,000, something like that, in the bank, and then we apply the A/F factor to that. However, we have to apply the market interest rate. So if we're expecting a real earning power rate of 4%, an inflation rate of 3%, we multiply those two factors together, subtract the 1, and get an expected market interest rate of 7.12%. And then we compute the A/F factor from that, 2,427,000, 262 multiplied by A/F at 7.12% for 30 years. That's going to give us 25,146. That's in actual dollars, and we would deposit those actual dollars each year. Let's look at the accumulation that we have. In year 1, the 25,146 is in there for 29 years at 7.12%. So that's going to generate 184,809. In year 2, the 25,146 is in there for 28 years. That's going to generate 172,525, and so on. The sum, of course, is 2,427,262, the same as it is in method 1. We should note, however, that the purchasing power of the deposit declines every year with method 2. This chart shows both the constant dollar valuation of the series of deposits and the actual dollars. Let's look at the constant dollar series for method 1. Method 1, we're putting in the same constant dollar amount. The curve that rises to the top here is the actual dollar series for method 1. So while we're depositing greater and greater amounts every year, in purchasing power, we're suffering the same amount. We're giving up the same consumption utility every year. Whereas with method 2, we're putting in an actual dollar amount that is the same from year to year. That's this line right here. But the purchasing power we're giving up with method 2 declines every year. Of course, it starts out the same, and then every year that purchasing power is actually less. So we're suffering less and less consumption utility that we're giving up. So those are two ways to compute the savings that we might need to put into a savings account in order to generate $1 million of purchasing power. Now, we already observed from the chart that the two approaches result in completely different deposit series. Oops. Other series are possible, such as arithmetic gradient, geometric gradient in terms of constant dollars, and so forth. Normally, when people advance in their careers, they get salary increases in terms of real purchasing power. In other words, their salary increases are greater than the rate of general inflation, and perhaps are able to afford a greater savings amount as the years go by. So you might have a geometric gradient in terms of constant dollars. If the analysis gets really complicated, of course, then you probably are going to want to use a spreadsheet to do the arithmetic. Okay, let's look at example 3. And here's where we're going to have differential inflation rates. We have a 6-year project with cash flows as shown in the next table. And we have a $10,000 asset in the 5-year property class. We're going to depreciate that asset using the alternative MACRS method, which is really a straight line method with the half-year convention. To keep things simple in this example, we'll say the estimated salvage value is 0. We'll take an income tax rate of 35%. That'll be the marginal tax rate. Maybe this is for a large corporation, and this particular project is just one of many projects. And we'll take a minimum attractive rate of return of 20% for this company when the inflation rate is 0. We'll assume a general inflation rate of 3% and some differential rates For example, we'll assume revenue inflation in that particular industry to be 7%, and we'll assume that labor inflation in that industry is 10%. And of course, we'll want to obtain the profit after tax, cash flow after tax, and ultimately the present worth. Here we have the data that's unadjusted, where we have some revenue estimates, 30,000, 35,000, 35,000 in the third year, 35 in the fourth, and so on, trailing off to maybe 18,000 in the sixth year. So this 6-year project ramps up fairly quickly, stabilizes, and then drops off rapidly at the end in terms of revenue. Labor expenses are fairly high in the beginning, and of course at the end of the project we want to cut back on the labor since we're not generating that much revenue. Material expenses have been estimated in this form. Then we can obtain our operating cash, take revenue, subtract from that labor, subtract from revenue materials to get our operating cash. So for example, 30,000 minus 20 minus 4 gives us $6,000 operating cash. And we do that year by year, just as we did in some of our other lectures. It's important to note that these values are not adjusted for inflation. These are the estimates that some project engineer or project administrator may have developed ignoring inflation. And we can do the cash flow after tax. I think we've seen this type of table before. We take our operating cash. The equipment depreciation is the alternative straight line method with the half-year convention. So in the first year, the $10,000 asset, remember this is in the 5-year property class, only gets 10%. In the middle years, years 2 through 5, we take 20% each year. The last year, another 10%. Our operating cash is already transferred here from the previous table, so then we subtract the equipment depreciation from that to get our taxable income. 6,000 minus 1 gives us a taxable income of 5,000 in the first year. 7,000 minus 2 gives us a taxable income of 5 in the second year, and so forth. The marginal tax rate is 35%, so we just compute 35% of each one of these. Subtract the tax from the taxable income to get our profit after tax. 5,000 minus 1,750 gives us 3,250, and so forth. And then last, to get the cash flow after tax, we would take the profit after tax and undo the arithmetic of subtracting depreciation. So in the first year, we take 3,250, add 1,000, and we get the cash flow after tax of 4,250. In the second year, the profit after tax is 3,250. Add the depreciation of 2,000, get the cash flow after tax of 5,250. Next, we want to estimate the present worth for this particular venture. This is an unadjusted data set, so there's no consideration of inflation, so we want to use the minimum attractive rate of return that is appropriate for this corporation for a scenario of zero inflation. So we simply take this last column, find the present worth of the last column at 20%. Of course, we must remember the investment at time zero of $10,000 for the asset. Now let's work with adjusted data. So we'll take a previous table where we had the estimates of revenue, labor, and material and inflate each one of those series by their appropriate inflation factors. The revenue inflation factor is 7%, so the time 1 original revenue estimate then is factored up by 7%. The time 2 original revenue estimate is factored up by 7% over 2 years. So that original estimate gets multiplied by 1.07 to the second power. The labor expenses are inflating at a higher rate. They're going up at 10%, so we take that original series and inflate it at 10%. Material expenses might be in the general category. The general inflation rate is 3%, so we can inflate that. So we adjust each one of these columns based on the differential inflation rates in this example. And then we obtain our operating cash in the same way. We subtract labor and material from revenue. So now our operating cash is given in actual dollars reflecting the differential inflation rates. Then we transfer this column into the next table where we proceed to do the same type of arithmetic. We've got operating cash. Our equipment depreciation remains the same. In the United States, you are not allowed to adjust the amount of depreciation just because there's inflation. So that stays the same. In some other countries, notably the countries that have experienced high rates of inflation for many periods of time, there may be provisions in the tax law where you're allowed to adjust this and claim more equipment depreciation. But in the U.S., you use the historical values. Take the depreciation, subtract it from operating cash, get taxable income. After that, the computations are basically the same. Compute the tax at 25%, subtract the tax from taxable income to get profit after tax, and then we get the cash flow after tax column by taking the profit after tax and adding back the amount for equipment depreciation. Of course, you can also get cash flow after tax by taking operating cash. We can take this value, operating cash, subtract from that the tax amount, and we get the cash flow after tax. That's another way to do it. Then we would want to evaluate this particular cash flow, and now because we're dealing with actual dollars, we have to use a market interest rate. So if the inflation-free minimum attractive rate of return is 20% for our company, we want to adjust that by the inflation factor of 3% to get a rate of 23.6%. So we'll take the 23.6% minimum attractive rate of return that's appropriate for these adjusted cash flows and compute a present worth of $5,905. If we compare that with the previous value of $6,773, we notice it's lower. And we might ask, well, why is it lower? Well, there are a couple of things going on. We've got differential inflation rates, and particularly the labor inflation rate is higher than the other rates. It's higher than the general inflation rate, and it's higher than the revenue inflation rate. That's one reason. Another reason is that the depreciation amount is not adjusted for inflation. At least in the U.S., that's not the case. So you lose a little bit of present worth there. And if we had a loan, the loan interest rates may or may not be adjusted periodically to compensate for inflation. It depends on the type of loan contract that you have. For example, if you have an adjustable rate home mortgage and there's high inflation rate, then typically the lending institution will adjust the rate higher. If the inflation rate goes down, they may adjust it lower. It depends on the contract and how fast they react and how many times the lending institution is allowed to adjust the rate. So let's summarize what we've done in this lecture. Basically, we've looked at some more involved examples where we showed the different approaches to inflation may yield different cash flow patterns. So you may have to play around with different approaches to get a cash flow pattern that you're comfortable with that satisfies your objective. If your objective is to build a retirement plan, there are many different cash flow patterns that can do that. So you examine different ones, most likely using spreadsheet analysis. If you have differential inflation rates, the effects may be not exactly intuitive. Sometimes the only way you can figure out what's happening is to actually crunch the numbers. And last, of course, the spreadsheets are almost a necessity for these more involved problems.